Hi, my name is Rob Hendrickson. I am a toxicologist and the program director for the Medical Toxicology Fellowship at Oregon Health and Science University. I'm going to talk about outdoor air pollution today. My objectives are to talk about what exactly are the contents of air pollution, what are the sources of air pollution, and then, of course, to describe the clinical effects and what health effects we should be aware of. So outdoor air pollution is simply gases and fine particles that are in the air that may cause medical harm, and they can be important. It's important to recognize they can be from both man-made and natural activities. Smog is a commonly used term. It's a portmanteau of smoke and fog, but not a very specific term, so it's generally just used as pollution, essentially. And, air pollution can be severe, and it can be severe in many, many different areas. This is an image of Bangkok. This is all smog or air pollution. This is an image of Beijing. But certainly closer to home, places like Los Angeles have in the past been famous for occasional smog events, and New York City. So all of these can happen. And even in places where we kind of think of really good air quality, this is an image of Salt Lake City with a thermal inversion, and you can notice the sort of reddish-brown discoloration of the fog there. That's pretty typical of air pollution. And then in my fair city, which is generally known for very good air quality, in the last 2 summers we've had events with a significant amount of wildfire, which has produced a lot of particulate matter in the air, and that's also air pollution. So this really can happen pretty much anywhere from a whole group of different events. But when we think about outdoor air pollution, we are specifically talking about several chemicals. And these are, in general, the chemicals we'll be talking about today: oxides of nitrogen, a lot of nitrogen dioxide, but multiple other nitrogen oxides. So we generally refer to them as oxides of nitrogen, sulfur dioxide or oxides of sulfur, ozone, carbon monoxide, particulate matter, and then a long list of hazardous air pollutants, which include a lot of metals and other chemicals that you may be familiar from other toxicologic exposures, but in this case, I'll talk about them in air. Now, just a story to start off. Story of London in 1952. This was a sort of confluence of events. This was a very cold week in London. So at the time, a lot of heat was coal burning, and so there was more coal burning, and the more coal burning leads to more pollution. It happened to be a thermal inversion and a particularly windless time in London, and so any pollution that was produced wasn't able to rise or be pushed out by wind, so it settled around the town. The descriptions of this event, the Great Smog of '52, are rather unbelievable. It got to the point where the smog was so thick that people were having difficulty walking along the sidewalk. They had to close all of the theaters and restaurants because the smog got inside, and not only could you not see the stage in a theater, but you couldn't see the person at the other side of the table in a restaurant. So all the businesses closed, and amazingly, this smog event has been associated with between 4,000 and 12,000 deaths in the city of London, and 100,000 people made ill. So these events can be very serious. They can increase mortality, and make a lot of people ill and increase hospitalizations. So with that in mind, that was a long time ago, and I think, but more recent events like in China in 2013, that upper right is an image out a hotel window at the city. So pretty severe event. This is a satellite image on the bottom right. That gray is smog. So this was an event that closed the airports because they couldn't see. Highways were closed due to poor visibility as well. So these events do occur, and these events can lead to not only disruption but also morbidity and mortality. So let's split a couple of our pollutants into primary and secondary. And what that means is primary pollutants are things that are released into the atmosphere. So sulfur dioxide is released into the atmosphere, and therefore a primary pollutant. It doesn't require other things to happen. These are sulfur dioxide, nitrogen dioxide, carbon monoxide, volatile organic compounds, and then many of the hazardous air pollutants. And I'll show you a list in a little bit, but that's like lead and cadmium and benzene and things like that. So those chemicals are just released into the air, and then we detect them. The secondary pollutants are a little different. They require primary pollutants to combine in some way to make a secondary pollutant. So, for example, ozone is generally not released. Ozone is a combination of volatile organic compounds, nitrogen dioxide, and sunlight. And those three things come together to produce ozone. Why this is important is because secondary pollutants are much more difficult to regulate, because if there's lead in the air, a primary pollutant, you can go and figure out what companies or manufacturing processes release lead, and you can go and regulate those. But if there's excess ozone in the air, you don't know if it's because there's a lot of nitrogen dioxide or because there's a lot of VOCs or it was particularly sunny and things like that. So all of these things are secondary pollutants, and particularly on the bottom there, acid rain, which is generally particulate nitrate and particulate sulfate. So you do need sulfur dioxide and nitrogen dioxide, or oxides of nitrogen, but you also need particulate matter. So the two of them together will produce those particulate nitrates and sulfates, and that would lead to acid rain. So these are the secondary. These are much more difficult to control or regulate, and require some combination of things. And this is just a schematic of what I just said. The first column here are things that are primary pollutants. So automobile exhaust releases carbon monoxide and VOCs and nitrogen dioxide, but only if you get VOCs, nitrogen dioxide, and sunlight do you get ozone. And so the ozone and particulate and the acid rain, the acid sulfates and acid nitrates, those are the secondary pollutants. So let me just go through individual agents. Sometimes air pollution means that all of these are increased, and sometimes it means just one of these or some small combination of these are increased. And, a good example of that is a wildfire tends to produce a lot of particulate matter, but not a lot of, say, ozone or carbon monoxide. So there are different scenarios where different agents will be the cause of your air pollution. Sulfur dioxide, SO2, the primary source is coal-powered plants. And so the problem with sulfur dioxide is that not only does it pollute the air, but it also combines, when it combines with water, like in your mucosal, like in your eyes and your nose and your throat, converts to sulfuric acid. That also happens in the atmosphere. And so it can cause mucous membrane irritation. It's a water-soluble irritant gas, essentially, and can cause not only the upper airway irritation, but also some bronchoconstriction. So you would imagine that a lot of exposure to a large amount of sulfur dioxide would lead to eye irritation and to, say, exacerbations of asthma or coughing and upper respiratory irritation. Now, nitrogen dioxide's primary source is automobiles. So also from power generation, so coal-powered plants definitely release nitrogen dioxide, but generally when you see a city that has a large amount of nitrogen dioxide, generally the primary source there is automobiles. So similar to sulfur dioxide, this can be an irritant. Now, the bottom right is an image of nitrogen dioxide, and you notice it's kind of reddish-brown. And if you see that reddish-brown discoloration, which I showed in some pictures before, that is a telltale sign that it's nitrogen dioxide, also, although it can also be particulate matter and things like that. But that is generally car exhaust. So just like with sulfur dioxide, combines with water in the lungs to form nitrous and nitric oxide. So, nitric acid, I apologize. And so leading to bronchospasm, airway hyperresponsiveness. And this is one of the reasons why, when there's air pollution in the air, you may hear on the news or on the radio or TV that people who have a predisposition to asthma or emphysema should not exercise in this air and things like that, because the irritants will increase their rate of exacerbation. Now, pull aside from medical toxicology for a moment and think about environmental effects a little bit. And there's a little bit of a story with sulfur dioxide and nitrogen dioxide. That is not as much of an issue now, but of course may come back and was an issue in the past. So it's important to recognize the history a bit. Now, sulfur dioxide and nitrogen dioxide are released by things like car exhaust and also by coal power plants, combine with particulate matter to make these acid nitrates and acid sulfates, and also produce sulfuric and nitric acid in the atmosphere, which decreases the pH of rain and snow. So the rain then falls, and you can imagine a low pH water solution falling on leaves may cause those leaves to defoliate. It may cause changes in the soil pH, which may change what plants can grow, and may change the pH in a lake, which may change what plants can grow and whether or not fish can survive. So acid rain was caused by air pollution. It was somewhat devastating for some areas of the country, particularly the mid-Atlantic states and the Midwest. This is an image of a forest that is coming back. It was destroyed by acid rain, so the leaves and the trees were died due to the low pH, and in addition to that, again, there were some events of die-offs of fish and plants and things like that, and change of the botany of lakes due to the change in pH. And in addition, acid liquid with water with low pH, in the form of acid rain, if it falls on limestone, can degrade the limestone. And there are many areas of the world where during the rainy season they have to cover up statues simply because this is what happens. You have a statue that is made of stone, and then it will slowly degrade as the acid rain problem increases. So an environmental issue that this is a map from way back in the early 90s when this was a much bigger problem. You can see the issue is sort of Midwest and Mid-Atlantic states and some of New England as well, where most of these events were happening in the U.S. So moving on to ozone, we always hear about ozone and the stratosphere being good, right? There was a hole in the ozone, and we're trying to fix that. We've done a pretty good job of that, in fact. But ground level ozone can cause some health effects, and so we want to decrease that as much as we can. So it's nitrogen dioxide or oxides of nitrogen combined with VOCs. All of these are produced from essentially burning things with energy production in automobiles, things like that. And then sun, and those three things combine, and so ozone, you can see, generally forms once you've got cars that are producing oxides of nitrogen and VOCs from energy production in automobiles and other other factories and things like that. And then afternoon sun. So generally ozone concentrations peak in the afternoon and are worse in summer when it's more sunny and things like that. This is a secondary pollutant and remains the most violated environmental standard in the U.S. In other words, we've done a really good job of controlling release of primary pollutants, but ozone's been really, really difficult to decrease. It's a low water solubility irritant, so it gets deep into the lungs, down to the alveoli, and causes pulmonary inflammation, so bronchospasm, and there's actually documented pulmonary function test alterations in days that have high ozone. In the short term, if there's a day that has, or a couple of days, you'll actually see an increase in admissions for pneumonia, COPD, asthma, and other respiratory complaints. This can be reversible, and one example of that is in Atlanta when they had the Summer Olympic Games. They reduced traffic into the city and were able to reduce ozone concentrations. So we know, and similar things happened in London and a couple of other cities that have tried this, where they decrease traffic into the middle of the city. You'll have ozone concentrations decrease. There are also an increase in mortality from cardiopulmonary disorders on days with high ozone. So this is not only an increase in hospitalizations from respiratory disease, but also an increased mortality in the short term, and in the long term, increase in chronic respiratory illnesses, and that's been shown even with lab animals. Carbon monoxide is released, it's a primary pollutant. I will not go into the details of carbon monoxide because I'm going to assume that most people listening to this have a really good handle on carbon monoxide. I'll simply say that it is elevated concentrations of carbon monoxide in the air certainly do correlate with carboxyhemoglobin concentrations or percentages in people, and different cities have a different average carboxyhemoglobin concentration at baseline based on the air pollution and some other factors in that city. So it's not hard to imagine that someone with an elevated carboxyhemoglobin concentration at some point may develop a cardiopulmonary disorder that they would not have, or at least would not have today, without that extra stress. Particulate matter is, as I mentioned before, released from diesel exhaust, but wood burning is a big contributor if there's an area that does a lot of burn piles and farms, also fireplaces, but also released from energy plants and cars, of course, even when they're burning gasoline. You can break particulate matter into their sizes, and this is really an important differentiator. So those particles that are greater than 10 microns tends to deposit in the upper airways, in the eyes and the throat. They can be very irritating. These are those events where you actually have particulates. You can feel them landing in your eyes and things like that. Your eyes get scratchy, but they generally don't go down into your airways, and so they tend to be more of a nuisance and a problem with visibility, a problem with eye irritation and mouth irritation rather than lung problems. Of course, particles that are between 2.5 and 10, and those are collectively called PM10s. So it's when you say PM10, you're talking about things that are smaller than 10 microns, and they tend to deposit in the lower airways, and then the really fine particles less than 2.5 microns, which are collectively called PM2.5s. Those can deposit all the way down into the alveoli and actually can have some systemic effects. Now, older literature and occasional things I see these days will talk about total suspended particles, and that is a measure of all of these things. So it's really a measure of what's in the air, all the particles in the air. But from a medical standpoint, from a increased morbidity, mortality, things like that, the more important things are PM10s and PM2.5. Most of the modern literature uses those numbers. So PM10s, again, smaller than 10 microns, increase in asthma and COPD exacerbations. It's not surprising if you put particles in someone's lower and upper airway that they have asthma, that they'll start having increased bronchospasm. So not very surprising at all. What is interesting is the smaller particles that get down to those alveoli does seem like they have several significant effects. One is increased mortality on days that have elevated PM2.5. So this is a really, really important aspect of outdoor air pollution, is that it actually increases mortality on days that have a high PM2.5 count. It's thought that it causes irritation and inflammation, which increases histamine release, which increases macrophage activity. There's actually an increases plasma viscosity, so not just lung effects, but also plasma viscosity, which may lead to increase in myocardial infarction in patients who are susceptible. Interestingly, there's a couple of studies that looked at PM2.5 concentration in the air and correlated those with increased defibrillator discharges and also with a decrease in heart rate variability, which is a marker for myocardial infarction risk. So these are the parts of outdoor air pollution have a very, very clear association with mortality. And this was shown in a very nice paper called the Harvard Six Cities Study, which correlated increases of particulate matter 2.5 with a 1.5. Every 10 microgram per meter cubed increase correlated with a 1.5% daily increase in mortality of all cause, which is a fairly large amount, and then an increase in ischemic heart deaths and COPD deaths as well. So moving on, hazardous air pollutants were established or introduced by the EPA in 1997. It's a long list of chemicals, many of which we recognize and are familiar with: benzene, arsenic, lead, mercury, those types of things, which all seem very reasonable. This is the 33 HAPs that are most hazardous to human health. And again, we recognize a lot of these compounds: cadmium, chromium, mercury, arsenic, lead, benzene. So these are specific pollutants that were specifically named by the EPA as hazards and are measured. So there are patterns to air pollution, and there are good days and bad days, and there are, if you look at the rush hour, you'll have an increase in nitrogen dioxide right during or after rush hour in both the morning and the afternoon. Ozone tends to peak in the sunny afternoons, and cold weather will increase sulfur dioxide and carbon monoxide and nitrogen dioxide from fuel consumption, both local and regional. So there are some patterns, and I put this up here because most areas of the country can have access to their air quality index. And this on the right here is just an example I pulled from my hometown, looking at the air quality that day, and you can see all those primary pollutants are listed on there, as well as the ozone as well. So should be able to find this for most areas of the country. Now, air quality index is an unusual scale, and it's over on the right there. What we want is good, and that means that there's a numerical value from 0 to 50, and that means that most people don't have to worry about the air quality that day. But as the numbers get higher, first from 51 to 100, they start talking about sensitive populations. So someone with severe asthma or severe COPD may develop bronchospasm from different contents of the air. And this is a scale from 0 to 500. Now, it's a couple of really important things. So in general, 100 is the PEL, and so unlikely to cause significant harmful effects below 100, but it's really important that the air quality index is the worst of any of the things that they're measuring. So if they're measuring nitrogen dioxide, sulfur dioxide, ozone, carbon monoxide, whatever the highest number, whatever the worst one becomes your air quality index. The other thing that's really important about this is not a linear scale. So 200 is not twice as bad as 100. It may be 10 times worse. It may be slightly worse. It all depends on the specific pollutant. And so it is not a linear scale. And though higher numbers are more pollution, a doubling of a number does not necessarily mean a doubling of the actual content of the air. So here I pulled a couple of these from from the internet. On the far left there, you see the air quality. Today's high, 53. That's moderate. And if you look down, directly down from that, down in this area, you see that ozone is good, particulate matter is 51, and PM 2.5 is 53. It is because of this number. It's the highest of the three, and that becomes this number. So tomorrow's high looks like it's going to be the same, even though the ozone concentration stayed the same and the PM 2.5s went down. So it's always the worst number that becomes the AQI. And here's another example where PM 2.5 is 71, ozone looks fine, but you're still going to get a 71 there. So a little bit about regulations. Mostly this is all driven by, there was an Air Pollution Control Act and then a Motor Vehicle Air Pollution Control Act, but then the Clean Air Act in 1963, which has been amended multiple times, has been the biggest driver toward clean air in the United States. The Clean Air Act established the National Ambient Air Quality Standards, and these were intended to protect public health, but also had a secondary standard to protect welfare. In other words, damage to crops. You saw all those issues with acid rain. You can imagine acid rain would decrease crop yields and potentially destroy crops and buildings and things like that. So all of these things are secondary standards. EPA is responsible for establishing and revising these standards, and the way that it works is counties are the air quality is measured in counties, and if a county does not attain the goal, then the state is mandated to develop a plan to bring that county into attainment. So it measures things at the local level, but then mandates the states to then develop a plan to make sure that that county is in attainment of those quality standards. So it also allows states to issue permits for large stationary sources, so energy production, coal-fired power plant, any large manufacturing that might use lead, and there's concern that it might release lead or release other pollutants. It gives the states the power to issue permits for them and regulate them. None of this should be memorized, I don't think, but just to give you an idea, these are some of the standards for U.S. ambient air quality, and these are the ones that they're measured against to see if a county is out of attainment. The Clean Air Act also determined criteria pollutants, and that's these 7 pollutants: nitrogen dioxide, sulfur dioxide, carbon monoxide, ozone, lead, PM 2.5, and PM 10s. And as I mentioned before, in 1990, the Clean Air Act amendment named 189 hazardous air pollutants, 33 of which pose the greatest threat to public health. And they have multiple phases of this act, but it requires all sources of HAPs to be established and also to be regulated. So again, factory, you want to build a new factory that may produce some pollutants, you have to be registered and monitored and regulated by your state. So air quality is monitored throughout the country. And if you look at, you can find this all on the internet for your local area. I pulled my city's information, and those 3 green dots are the air quality sampling stations in our area. There are a couple more north up in Washington as well. So we can look at any time and get real-time readings of air quality. So this is an example. This aqicn.org will give you air quality for most areas of the country, and in fact, not just in the country, but internationally as well. It's a pretty interesting website. I highly recommend it. And if you can't find this website for your area, then just Googling air quality in your hometown or a city that's near you should give you this information. This is just, as I said, I just pulled this on one particular day. You can see the patterns of PM 2.5s and ozone and nitrogen dioxide, et cetera, et cetera. On this day, our air quality index was 30, and that's good. But you can see that different areas of the city have different air qualities, and this is particularly interesting when we had wildfire smoke, where you could see areas that would become poor, and then it would sort of move in one direction or the other. So very interesting, but really helpful to find out about real-time air quality pretty much anywhere in the country. So, a lot of regulation, Clear Air Act, has it worked? And the answer is a resounding yes. There's absolutely no question. So, I'll show you a couple of these graphs are really fascinating. This is the top one is nitrogen dioxide. This purple space is the range of counties, the concentration in counties in the United States, and the white line is the mean. So the mean was a little over 100. They established a national standard of 100 parts per billion, and you can see with regulation over time, 2 things have happened. One, the national mean has dropped tremendously, almost by half, and the second is that the range has gotten much, much more narrow, and the vast majority of sites are below this standard now. PM 2.5 had the exact same response. Lead, tremendous variability and very high mean concentrations in 1980 that have now decreased. You can see how compact that range is now. All hovering around the national standard. Ozone been much, much more difficult, mostly because it's a secondary pollutant, so it's much more difficult to specifically regulate. But ozone concentrations have decreased over time, and we are making progress there. So what have been the effective things, and what have been the successes here, and what could be done to decrease air pollution further? Sulfur dioxide is mostly the concern is coal-fired energy production. So there are reduced sulfur coal as well as reduced sulfur gas and diesel, which will release less sulfur dioxide. Obviously, engineering controls at energy production facilities. There have been several regulations of automobile pollution as one of the main reasons we took lead out of gas several decades ago. Benzene concentration in gas has been reduced and regulated. And also adding oxygen content, like adding ethanol to gasoline, will make the gas burn cleaner and produce fewer contaminants or fewer pollutants. And then also decrease in the amount of sulfur in gasoline and diesel. And then, of course, automobile emission standards go hand in hand with those. The advent of the catalytic converter in 1975 was tremendous in decreasing air pollution from automobiles. The catalytic converters combine carbon monoxide with oxygen to form CO2, which isn't, from a climate change standpoint, isn't great, but it is certainly in the acute stage or better than carbon monoxide. Also helps to clean unburned hydrocarbons and, in some instances, reduce nitric oxide as well, nitrogen dioxide, I should say, as well. So these are tremendously effective and have been in use for several decades now and probably contribute significantly to the decrease in automobile emissions. So also fixed site, the EPA's fixed site polluters, the regulations have led to engineering controls. There are some things that can be done that would potentially be, there's some research on catalytic converters for smokestacks, which is fascinating, but have not yet been economically feasible to be put in use in large quantities. So, and obviously looking for alternative raw materials and catalysts and things like that. So air pollution is a complicated mixture. Primary pollutants and secondary pollutants can lead to increased respiratory complaints and infections, increased mortality on bad air days, and that's the reason why we have that air quality index and the reason why the news or the TV or the radio gets on the phone, gets on and says you shouldn't exercise in this weather, et cetera, et cetera. And of course could be controlled with strict regulation, and remember that it's monitored in real time in many locations. So, air pollution is something that can happen anywhere, even in my fair city, where we consider our air quality to be pretty good. Wildfire season brought us a fair amount of particulate matter. So this is a problem everywhere, and it's an important problem. It's an important problem for toxicologists to contribute to solutions. Thanks so much for listening to me. I hope I helped in your understanding of air pollution.